Hello, my name is Gerard O'Reilly. I'm an Associate Professor of Structural Engineering at IOSS Pavia in Italy. And today we're looking at the Djura online platform, specifically the hazard module and the options for ground motion record selection that are available within that. So if I click in here, I can have a look at these really quickly. So we had some other videos in the past where we're looking at the first two options you can see here on the top of the screen. We had the uniform hazard selection, which is matching the typically the building codes or other kinds of spectra that are based on uniform hazard. We also had the unconditional selection, the generalized version of that, where we had different kinds of intensities and how they can be how the target distributions could be matched based on the input earthquake rupture scenario. So what we're looking at today is what's called the conditional selection. So it's probably better known as the conditional spectrum method, but this is a generalized version of that, where essentially what we're doing is we're conditioning on a single intensity of a conditioning intensity measure. So based on that, we construct the other secondary IMs, we'll call them today, okay? And this is based on the correlation models, ground motion models, contributing earthquake rupture scenarios, and so on and so forth, okay? And this is probably the best known method because it's used in multiple stripe analysis, so it fits in quite well with building code requirements and also PSHA and disaggregation outputs. So let's click here and get started with this. So one of the first things we need to do when we're doing a conditional selection is to know the intensity measures we are interested in, okay? So when we're doing a conditional selection, we have a conditioning intensity measure, of course, but also we want to know about the other intensity measures we want to condition our ground motion selection on, okay? And in order to have the appropriate probabilistic distributions of these intensity measures, we also need ground motion models to predict these distributions, okay? So what we do first is we add these IM GMM pairs. And what we can see here on the window is that this little menu pops up where it asks us which IMs we are, or which intensity measures we're looking to do our conditioning on, okay? So we have some pretty popular intensity measures here, like significant duration between 5 and 75% of the RS intensity, filtered incremental velocity, which is a relatively new intensity measure, and also classic ones like peak ground acceleration, peak ground velocity, spectral acceleration, and also average spectral acceleration as well, okay? So we're just going to go for a classic one here, like spectral acceleration. And we can see that the option appears below about which ground motion models we want to use to represent this intensity measure. The default value here is Aristedo et al. 2014, but we can remove that and we can just pick some other, let's say Boer and Atkinson from 2008, and possibly even another one, let's say, we'll pick another one down here from 2008 as well, okay? And what we can see here is that for this intensity measure, we can see that these ground motion models are forming, let's say, a logic tree, and they're equally weighted here. We can see if we hover over, it's at 0.5, and we can adjust these weights here as well if we want to adjust these to be, let's say, 0.6 and 0.4 in this case, okay? So we can see that these have adjusted based on the inputs we have. So what we've done here is we've defined an intensity measure that we're interested in and how we're going to model that with the GMMs we've selected. So the next thing we can do, we could technically do our selection just based on spectral acceleration, but the nice feature about this is that we can add different intensity measure types as well, not just spectral acceleration. So this is not just the typical conditional spectrum method, but also what is generally known as the generalized conditional intensity measure approach, the GCIM approach, okay? So here we've already selected the spectral acceleration using these ground motion models, but we can also select some of the other available intensity measures that we had here. So let's do a simple selection where we're going to condition on peak ground velocity, okay? And again, we have the default ground motion model just to get you started is this one here, but let's add in another one here. So Binde et al. 2011, and possibly even Boer Atkinson 2008 as well, okay? So we've added 3 ground motion models here for this intensity measure, okay? We can adjust the weights, but let's just leave them equally weighted, okay? And finally, we can add a third one. We can add as many as we like, but of course we complicate the analysis then. But let's just add a third one in here where we look at the significant duration between 5 and 75%. And here we'll leave in the default model. We'll just add in this Bomber et al., for example, and we'll leave these 2 models here like this. So basically what we're doing is we're going to do a ground motion record selection, which is going to be conditioned on these 3 intensity measure levels, okay, and using these ground motion models with the appropriate weights like we've shown here, okay. So we can save those, but also we can do something very quickly here, which is we can download these intensity measures and the ground motion models to what's called a JSON file. So this is like a dictionary format in a text file, and it can basically just represent everything we've input here to the screen in front of us in a text file, and we can modify that, let's say, a bit more programmatically ourselves on our local machines and use them in just a moment. Another nice feature is all of these little logic trees you can see down here. There's the option to you can interact with them, you can collapse them down, you can also save the images, and so on and so forth. So these are quite handy as well, just for illustrating what it is you're doing during your ground motion selection. So let's say we're happy with this set of intensity measures and the ground motion models we want to use to represent them. And let's move ahead to the next section, which is the rupture scenario. So in the rupture scenarios, we'll be asked for a couple of input parameters. So these parameters really depend on the ground motion models we've chosen at the previous step. Okay, so some ground motion models have different amount of input parameters than others. So depending on the ground motion models we've chosen, this menu will update accordingly, okay? And one of the first things we're asked for here is the site context. So this is not necessarily a rupture parameter. This is just a site parameter that depends on the site location of our building or the structure we want to analyze, okay? So in this case, the ground motion models that we're using require these input parameters for the site, okay? So we're not going to go into detail about the parameters here, but we can see that by hovering over them, we have a quick idea of what they refer to. And of course, you can look at the reference publication for more details on what they refer to. Here we have some default values just to get us started, but of course you need to update these depending on the analysis that you're looking at. For this case, we're not going to change anything. We'll just save those, and we can go to the next step. So the site parameters have been saved here. So what we're going to do now is we're going to add a scenario. So this is a rupture scenario. So what we're doing here is we're defining the earthquake rupture scenario we want to consider in our selection, okay? So this is going to be the main rupture scenario that's going to be contributing to the conditional selection. And again, like I mentioned before, the input parameters depend on the ground motion models that we had. So these are divided into rupture context and also the distance context with respect to our site, okay? So we have some default parameters here, like the magnitude, for example, 7.5, the rake, dip, and so on and so forth. These are just values to help get you started. But of course, you need to go and update these depending on your own specific context. So we could save those. But the nice thing now is that we could add a second scenario. So instead of just looking at the dominant scenario that we have in our particular ground motion selection, we can add several of these. So we're not forced to look at our disaggregation of PSHA results and pick, let's say, the mean value or the modal value from the disaggregation, but we can add all of the contributing scenarios. So in the case of this one, like we had here before, we had magnitude 7, distance between 10 and 15 kilometers, depending on which distance parameter you're using. But right down here, we could look at something slightly different, so say something like 7.8, for example, and we could save that. Now here we're just looking at, we're going to input two different scenarios and we're going to equally weight them. We could, these are weighted as 1 and 1, but the program automatically normalizes all of these, so it's not an issue. Inputting the entire disaggregation output and the individual magnitude distance pairs and the corresponding contribution can obviously become a bit tedious. So the nice thing here is that we can download the scenarios into a JSON file, and we can see the format of that, and you can modify that yourself locally, and you can basically convert your disaggregation output into this format and upload it here with this little button we have shown on the right hand side. Okay, so instead of doing this graphically every single time, you can adopt a more programmatic way to do this. Okay, and we're also working on a patch with some other softwares where you can just directly upload your disaggregation information for softwares like. So once we have this finished, we can go ahead and we can check and validate our input data. Oh, no, we can't do this because we're missing the final parameter, which is the conditional intensity measure. So what we've done so far is we've just said, these are the intensity measures we're interested in. These are the ground motion models we're going to use, the relative weights between them. These are the scenarios, the site context, and also the different scenarios with the rupture and the distance context. We've saved all of these, and that's fine. But we also need to define which one of these intensity measures is going to be the conditioning one. So which one are we going to base all of the other distributions on? Okay, so we come here, we can have a list of the available intensity measures that we can pick from. Okay, so let's go for, let's say, spectral acceleration at 0.5 seconds. And we'll say the conditioning value that we found from our PSHA was 0.5 G. Okay, so we can just input that value, and that's fine. We come back over here, we do our validation, we can see that we have everything to get going. Okay, now we can come down here to our logic tree. So the logic tree is essentially representing all of the inputs we've just put in there with respect to the intensity measures, ground motion models, and also the different ruptures. Okay. So if we scroll down here, we can first see a table, right, where we can see all of the different input parameters. All of this this is represented here. We can scroll across and we can see many different of the different rupture parameters and different combinations. Okay, we can download again this into a JSON file. We can see this on our local machine, but probably the most appealing version of this is the graphic illustration that we have here below, this this interactive thing where we can see the different rupture scenarios and also the different intensity measures that we are accounting for here. And if we expand these out, we can see the different ground motion models that we're using, and we can also see the relative weights between them, so the total weight depending on the different contexts. Okay, so it's possible to expand this entire thing out, and you can see the logic tree grows quite big, very big quickly. But it's also a very nice representation of what it is this ground motion selection is going to be based on. Okay, so one of the things you can do is you can save this as an image by clicking on this button over here. It will save an image that you can use in your presentations, reports, just to describe what it was you did for your ground motion selection. It's a good summary of all of the parameters. Also, this table can be quite useful. You can look it up by searching for certain GMPs if you wanted to check out the weights or the parameters that were used, and so on and so forth. Okay. So once we've done that, we're essentially ready to identify our target, okay? And the last thing I'm going to show you over here on the right-hand side is this is show logic tree. This is essentially the step that we're at right now, but also download all of the input data, okay? So this is useful because I've shown at the previous steps, you can download the, for example, the IM, GMM pairs, you can download the rupture scenarios, and so on and so forth. You can download the logic tree, but if you hit on download all input data, it essentially downloads all of this into a single JSON file, and you can see all of your input data in a single place, right? This is going to be quite useful because it gives analysts who, let's say, don't want to use a user interface every time, it gives an idea of the required format that you can directly upload all of this, and you can get started relatively quickly. The nice thing about this is that it will be callable through API, and basically you can integrate this framework, this ground motion selection tool, directly from the web into your local machine. So your local workflow, let's say in a Python environment or in MATLAB, for example, by calling this through API. So with the right commands and the right input data, you can basically request and call this the outputs of this tool directly from your machine without necessarily having to go through the user interface. Of course, the user interface is nice to see what is going on, learn how it works, and develop the basic input data for the first time, so you can get familiar with it. So, like I mentioned, we're ready to go, and we can do our creation of the target distribution. So this is something we'll do, and everything has been validated, and we have created our target distribution. Okay, so this is when we come over here and we can see the first set of figures we have based on this target distribution. So given that our conditioning intensity measure was a spectral acceleration at 0.5 seconds, it makes the most sense that all of these are pinching. They all have a zero dispersion around this point here, and we can see the pinching point and the dispersions at the other periods away from this. Okay. So we can see the spectral acceleration is plotted in log scale, hence the negative values. And also we have period here. We also have the non-period dependent IMs over here that we're looking at for the different branches of the logic tree. And the nice thing about this plot is we can turn off and we can turn on specific branches, and we can see exactly what it is that we are looking at here. So for example, if we want to turn off all of the cases where we have the plus and minus 2 standard deviations and just look at the medians, we can see something like this here. This is also shown below. Or in case of the different dispersions around the medians, we can see the differences between those with the respective branches of that. We can zoom in as well here. So if we click on this here, we can zoom in relatively quickly, and we can see we get we can look up some values of the plot just right here on the spot. Also, we can look at the data view, so we can look at the tabulated values. So this is quite handy as well if you want to just check a quick value and see what the values would be and the differences between them. You can reset the plot, okay, like it was initially when we opened the page. And the last one is we can save the image as a picture on our local machine to use however we like, okay. Lastly, down here, we can see some standard plots. We can see the different branches of the logic tree we had, so the different targets basically, and the combined mean, sorry. target distribution, and also the standard deviation for the spectral acceleration, right? So this is basically our target distribution. We can download this as well. Like I mentioned before, you can download all of this information to store it locally, so it's you have some idea of what numbers we're talking about, and save all of these images as well, right? So the next step we want to go to before we do the record selection is looking at some of this advanced input we have over here, okay? So what we're looking at here is the advanced input parameters and maybe some other computational settings we might want to adjust or just tailor based on our specific needs. So we have the advanced selection settings. So depending on the components we're looking at, we have 1 or 2 components here in this option here. We're currently working on the vertical components, so that'll be available pretty soon, but also the different intensity measure component definitions. For example, the geometric mean, the rho D100, rho D50, the number of ground motions we're looking to select, and also the significance level of the KS test that we will implement. The scaling we want to limit, we can set the scaling as 3, for example, or we can have no scaling. That's also an option. This is the computational settings over here on the right hand side. So the amount of loops we do to optimize our record selection, the amount of work the computer needs to do. So obviously if you increase these numbers, it may take a little bit longer to do a record selection. And let's say we want to pick, instead of 40 ground motions, we want to pick something like 50 ground motions. We just go ahead and save that. And the next one we want to look at is something that hasn't been mentioned yet, is the list of intensity measures. Okay, so when we pick the intensity measures we want to look at, we just pick the intensity measure types. We didn't give any specific information about the periods we were interested in for the spectral acceleration, for example. So this is something we can modify here. Some values were automatically compiled. You can see this here, for example, 0.1, 2, 3, 5, 7, 1, and 1.5, and all the way to 2 seconds were picked automatically. These are the relative weights between them. But let's say, for example, we're also interested in looking at 1.2 seconds, for example. So we can just come over here, we can enter in 1.2, it automatically gets added to the list, the weights adjust accordingly. And also we can add in something like, let's say, 0.6 seconds. Okay, and also 0.4 seconds. So we can add a few more spectral accelerations in there just for the sake of having them in the plots. Okay. And the same thing with the search limits over here. So this is the last feature. So this is basically a filtering criteria for the ground motions that we're going to have as candidates for our record selection. Okay, so for example, if we only want ground motions that are coming from a certain kind of mechanism, we know some of this information from our disaggregation. We can select only strike, slip, fault, for example, or we can do something else. So let's say we only want strike, slip, normal, or reverse fault. So these other options down here, we're not going to consider ground motions that came from those kinds of earthquakes. The same thing with the magnitude. So let's say we only want magnitudes between 5 and 8. It's a pretty wide range, but okay, it's something we can input, and we just save those. Okay, and because we added these different intensity measures, it's a good idea just to recreate the target distribution again. So we can come back down here. We can probably see that we've added in another point here, just around 0.5 seconds. We added in 0.4 and also 0.6, so we can see that the plot is slightly changed as well. But now we're ready to go. We can do the selection of the ground motions. We come over here and we hit perform record selection. And you can see just in a quick second, it selected all the ground motions, all 50 ground motions. We come over here and we can see this on the screen right in front of us. So essentially what we have here is we have a plot of the spectral acceleration versus period. We can see the selected records, the median, the target, and also the percentiles around that. And we can see, we can look up particular values. We can turn these off. We can look at just these values here, and so on and so forth. Look at the tabulated data like we had before, and of course save the figure, which is always handy. Moving to the figure below, we have the cumulative distribution function, so the cumulative probability of each of these different intensity measures we were looking to base our selection on. So for example, up here we had the selected records. We can turn them back on for a second. And if we consider the point of 0.1 seconds, which is around here, for example, so we can consider let's say the vertical stripe here, and look at the probability distribution of the selected ground motions and also the target that we had initially. And this is what we're plotting here below. Okay, so we can see the empirical cumulative distribution function for the selected ground motions, all 50 of them. So we can see 50 is written here. Also the KS bounds based on 5%, and also the target distribution we were looking to match. Okay, so we can see here that it's within the bounds, everything's looking good. So we can be relatively happy with that. In the case of the other intensity measures, we can quickly look at those. We can look at 0.3 seconds. Again, the matching is looking great. 0.5 seconds, which was the conditioning value. So we can see we have no dispersion here, which makes sense. And in the case of 0.6 seconds, like the additional intensity measure that we added, again, this is looking great. But probably the nice feature of this is we can look directly at intensity measures that are non-spectral acceleration. So essentially the generalized conditional spectrum approach, okay, to record selection. So here we can see the distribution of the peak ground velocity. Everything's looking great, it's within the bounds. And the same thing as well for the significant duration. So this is all done with just a few clicks, okay? So lastly, probably the most interesting part of all of this is obtaining the actual records. You can download the selection outputs. So this is just a summary of what's shown on the screen here. But probably the most interesting part for anybody using this tool is downloading the scale records, okay? So this is a list of so we selected 50 ground motion, so we can say 1 to 50. This is a simple table outlining all of the different earthquakes, all of the different parameters that we're looking for. We have the names of the files, so on and so forth, and the scaling factors that were used for each one of those, okay? So to obtain this, essentially all we do is we just click on download scaled records. And what this does is this just provides a single zip file with all of those file names inside, a little summary, and also gives us some information about the selection that we've just performed. So these are the scale records ready to go in your nonlinear time history analysis. And that's pretty much it. So essentially what we've looked at here is a pretty simple tool, pretty fast tool as well, that we can use to perform our ground motion record selection. So hazard consistent with the disaggregation, PSHA outputs, and it can match the target distributions of all of these different intensity measures that we're looking at here. So not just the spectral acceleration, but also other ones like duration, velocity, and so on and so forth. And so this is essentially the generalized conditional record selection approach. And this can be used directly in things like multiple stripe analysis as is required by some guidelines like FEMA P58 if you're doing a loss assessment, for example, or other guidelines around the world. So this approach can already be used by several design codes around the world, for example in the US, also in Europe, as part of site-specific studies and more advanced record ground motion record selection. So it's something that is being integrated into different approaches around the world, and something that hopefully with a tool like this becomes a bit more accessible and a lot more easy to implement. So we've tested this. We're adding a lot more features as we speak. So a few of them I mentioned during the video. If you have specific requirements, just let us know, get in contact. We'd be happy to add them. We plan to extend the ground motion databases as well, so we have a lot more candidates, even though the selection we just did on the screen right now wasn't much of an issue. Also ground motion models and things like that. So this video summarizes how to use the user interface, but obviously in a more programmatic way. It could be a lot more convenient for a lot of people. So like I mentioned before, downloading this first sample of input data is probably a good way to learn to know how to use this thing a bit more programmatically. So the nice thing about this is that within your local Python or MATLAB environment, you can basically go and call this tool and do your record selection directly from there. So with a couple of with a little bit of coding, you can link your disaggregation, you can link your hazard analysis, your record selection, and even your nonlinear time history analysis within the same environment. Okay, so the idea is to fit this in pretty effortlessly into your workflow. So this is just one of the ground motion record selection approaches we offer. There are a couple of more videos describing the other ones. So if you want to know more about those, just go and check out the videos. If you want to know more about us, come visit the website, drop us an email, however you want. Follow us on LinkedIn. And yeah, stay tuned for other videos and other apps on the other applications shown on the top left here. So these are the hazard-based ones, but we're also working on different apps as well that can help you out in these other different areas of risk engineering as well.